Hello and welcome in the online lecture series of BTech Mechanical 4th semester Strength of Material subject. We are discussing bending moment diagram and shear force diagram. We have covered all the types of beams and different combinations of loading, and we have studied till now how to draw bending moment diagram and shear force diagram for different types of loadings and different types of beams. So today we will be concluding the session, in this session in this session we will be looking overview what we have studied. We'll have a quick overview and quick review of we have studied in the last 5 lectures. Today's fifth lecture in this shear force diagram and bending moment diagram, and I hope everything is clear by now. Still I am giving an overview so that you again refresh your whole knowledge and how bending moment diagram and shear force diagram are drawn. So in case you are having any difficulty, you may get in touch with me through phone and WhatsApp call. My phone number is 9069360400. So as we have discussed earlier, again I am going to give an quick overview of shear force and bending moment diagrams. So I told that shear force is a force that basically acts into a two opposite directions on the surface of the object, so that it tries to tear the part or component. So shear force is a force that basically tries to tear the part, to tear the beam or wherever it is being loaded. So there is a shear failure among the slip up planes, and these two slip up and this slip up plane is somewhere between these two opposing opposite nature of shear forces. So shear force is always combined by an opposite direction force, and these two try to tear the body from a plane that is called slip-up plane. Here we can see that this force is acting downwards, and another force is acting upwards, and this way the force will tear from somewhere in between this body and the CD cross section. This is the example where we can see that this is support and this is beam, and beam is basically used to transform and transfer the loads acting on it. So this is the beam, and this beam is giving this beam. This is the beam, and this is column, and this column is giving vertical upward support to the beam. So the beam is facing this force. Beam is subjected to a vertical upward force. At the same time, the beam is loaded. So the other loading is done. So this is the load on the beam, and here there is no support, only this point we have support or column. So the force is acting on it in vertical downward direction. So you can see we have a couple, we have a equal and opposite direction forces acting on this column beam, and this will try to tear the beam from somewhere in between these two forces. So this is the shear force. So first, sign convention. How shear force is studied? Shear force studied, we have earlier discussed shear force if we have to check the beam, and if in the left portion of the beam the shear force is acting upwards, the sign convention is positive. Otherwise, uh, the in the left section, if the force is acting downwards, the shear force is negative. Similarly, we can see in the right portion, the shear force, the resultant force must be acting downwards in order to be it positive, and vice versa is also true. In the left section, if the resultant force is acting vertical upwards, the shear force is negative. So this is the sign convention and concept of shear force. Now we'll discuss the sign convention in detail. We can see here, if we are having in the left hand section, the force is vertical upwards, so this is positive, and again this is negative. Sorry, this is positive and this is again negative. We have to check left portion, and if it is upwards, the shear force is positive, and if in the right section, if it is acting downwards, the shear force is positive. So negative in case, the reverse case, if in the left section it is acting downwards, it is negative, and right section it is acting upwards, it is negative. So this was the shear force. Bending moment, as we have discussed, bending moment is basically a moment, and moment is a product of force multiplied by perpendicular distance. So we have got a shear force, we have got a force, and this force is multiplied by a perpendicular moment is known as bending moment. So moment is bending moment is a moment that tends to bend or sag the body, and it does not let the body in its original position, in its horizontal position. So this is called bending moment. This is sign convention. Sign convention is very, we have discussed earlier, that if the body is bulging, if the beam is bulging like that, the center point of the body, if the center point of the body is going downwards, the beam is such deflected in a way that the center point of the body is going downwards, it is called sagging. Or the curve, or the curve, or the convex face is beneath the top portion and it is facing earth, it is known as sagging. And this way we have two faces. The top the top face is under compression, whereas the lower face is under tension. This position is called sagging and the bending moment is positive. Whereas the reverse condition, in which the top portion goes up or the convex face is facing the sky, it is known as sagging. Hogging. Hogging has bending negative moment. Hogging is negative bending moment, and the lower surface is compressed, the top surface is expanded or in tension. So this is called hogging and the bending moment is negative. Okay, so this was the sign convention for shear force and bending moment diagram. Will be coming, you can see like this. This is the resultant moment of left hand side of the x section in clockwise, then it is positive bending moment, and resultant moment on the right hand side is counterclockwise, then it will be considered as positive bending moment. Either we can take left section or right section, and if this is the condition, we will be taking positive bending moment, and again we will be considering left or right section of the beam, and if any section is going like this is known as negative bending moment. So first we will take cantilever beam, and in cantilever beam we will be loading point load. So in point load, when we are having a point load, the free end B will come down. So this way we'll have this position, the free end will come down, so this will have right side right side downwards, and so the bending moment will be negative. Whereas shear force diagram, we can see that shear force diagram is left hand side downwards. So left hand side downwards is positive shear force, we can see here. So bending moment, so a cantilever beam with point load on free end will have positive shear force and negative bending moment. So this way we can find the bending moments and we'll calculate the bend. This is the shear force convention and the bending moment. So we will find this is the shear force, and shear force is uniform from this point to this point. We have earlier discussed that shear force will be positive. This is the baseline AB, and we are having a shear force P. So from here to here, there is no other force except this P, and at this end we are having a vertical support. So from this point to this point, we are having only one force, that is equivalent to P. So we'll draw a line equivalent to P. If P is 10 Newton, we'll assume 10 Newton is equal to 10 millimeter. We'll draw a line 10 millimeter, and this is the length of length of beam. This is called length of span, that is clear length between two supports. So if it is 20 meter, we will take 20 millimeter and we'll draw a line 20 millimeter, then 10 millimeter, and from here to here we will draw a line parallel to this line and we will join. This is here for diagram. Then we have negative bending moment diagram. As we discussed, we have negative bending moment diagram because right section is vertical downwards and hogging is there. So hogging, for the hogging case, bending moment is negative. So from here to here, we will be having bending moment from this point P into 0. The bending moment is moment. So moment force multiplied by distance. So this is acting force P and P multiplied by 0 is 0. So this point will be having 0 bending moment, whereas this point will be having maximum bending moment because P into L, if it's 10 Newton and if it's 20 meters, so 10 into 20, 200 Newton meter will be maximum bending moment, and this will be 200 mm, 200 Newton meter, and this 200 Newton meter bending moment will be represented in terms of distance. So this will be 20 millimeters. So we'll draw this length of span 20 millimeter and this one is 20 millimeter, and we will join from here to here. So this will be a degree higher. This is slightly increasing. We can see the force is applied all of a sudden and there is no other force. So the this way we'll have the shear force from here to here, and it will be constant from here to here, but the bending moment is constantly changing. The bending moment is constantly changing. We can see P into 0, P into 1, P into 2, P into 3, P into 4, up to this point P into L. So this way bending moment will constantly increasing and it will be straight line from here to here. So this was the case of shear force and bending moment diagram on a cantilever beam with point load. Similarly, we have a distributed load. Distributed load is also taken while considering the bending moment and shear force diagram. So in uniformly distributed load, it can be converted into a point load for all practical purposes. So UDL is acting at the center of the beam, while we have to replace UDL into point load. So this is given at load or force per unit length. So this is W kilonewton per meter, and the total load will be W into L, and this will be acting at exactly at the center point of the beam. So we have to replace this UDL with point load while we have to calculate the shear force and bending moment diagram. So we can see this is the reaction, this is the shear force. Here we have to again we can see the right section will have direction upward direction, and the left section will have left section will have upward direction, and right section has nothing, no direction, because this point is not under any force. Only force is starting 0, 0, 0, 0.1, 0, 0, 0.2, 0, 0, 0.3, 0, 0, so on. So this way we are not having any force on this point. So this point is feeling forceless. So this is shear force will start from here 0, and this will be maximum to this point. So W into L, so this is W into L, and this will keep on increasing till here, and shear force will be positive. Similarly, bending moment will be negative, we have discussed earlier, and this will keep on decreasing from here. This will be here will it will be negative, there will be 0, and then it will keep on negative, and this will have minimum bending moment. So from 0 to this will be W into L acting at L by 2. So W L into L by 2. This is WL square by 2. This is bending moment, and this will draw from here to here is a parabolic curve because it is a second degree order of equation. So we are having a quadratic equation where length is having second order. So in second order, we are having first different from first order. In first order is straight line, and in second order we are having a curvilinear. So this was the case, and we will draw. We can draw now combination of these two. So we have to do it on our own. So we have to practice. So we can see these are the conditions, and these are the reactions, different types of conditions we have to. For example, this in this example, we are having point load combined with uniformly distributed load. and this is the shear force diagram that we have discussed earlier. So this is the bending moment diagram that we have to do on its own. We have to solve many examples, then only we'll be able to draw bending moment and shear force diagram on our own. So these were the different combinations that we have studied, and we'll have to solve it. Now, in the second section and the second example, we will take this is the we will take bending moment diagram and shear force diagram of a simple supported beam. Simple supported beam is a beam which is supported on both the ends. This is the simple supported beam, and combination is given is point load. This is the point load is acting. So we are having on our screen two forces are acting vertical upwards. One is this at this point A and another is at point B. So this is point load, this is roller support. So this is also point load. So we can see this point load vertical upwards and this vertical upwards. Since beam is not subjected to any horizontal forces, so we are not going to take any horizontal components. So RAH will be 0 and RAB plus RB must be equal to P, because P has to compensate. P is divided on both these two reactions, so RAB must be equal to RB, or sorry, RAB must be, or AB plus RB must be equal to P, and by taking moment about any point P, we know RAB and RB. So this will be RAB will be P into B divided by L. Similarly, RB will be P into A divided by L. We can find these reactions here. Simple. So this is the shear force diagram for simple supported beam along with point load. We can see here we are having on our left we will see PV by L, right side PV by L. These two are reactions. P weight is particular vertical downwards. If we check left side section, we will see that if we cut the beam from here, we will see there is one reaction vertical upwards, and if we cut the beam from here, we will see there is also action from vertical upwards. So this vertical upward reaction is giving us negative shear force. You can see here in the side dimension, and this section is giving us positive shear force. So we have a baseline AC, and we from here to here we will draw a line equivalent to PA by L, and this is negative as we discussed earlier. So from here to here we are not having, from C to B we are not having any force except this PA by L. So this line will be straight PA by L, and at PA by L we will be having a jerk of P from here to here. So we have to draw a line from this point to upward direction, and from here to here it will be remain constant, because P is reaction only and there is no other force between P and PB by L. So this way we are having right side shear force negative, left side shear force positive, and similarly is the case with bending moment, and bending moment starts from here to maximum here, and then here P is the PA by L into 0, and again this PB by L into 0. So these two point A and C will be having 0 shear force, whereas this point will be having maximum shear force. So this point is PAB by L, PA by L into B. This is the distance. So force multiplied by distance is PAB by L, force multiplied by distance. So this is the moment. So at this point we'll be having shear bending moment PAB by L, and we can calculate from this side also. PB by L is the force, and this will keep on increasing up till here. So PB by L into A. So this will be PAB by L, and this will keep on increasing from here to here, from here to here, and this is of 1 degree. So this equation is representing 1 degree, or P, A, and B all are single degree. So this will be having a straight line, whereas in case of UDL we will be having bending moment of second degree. So this is the case of bending moment. This is the case of shear force diagram with uniformly distributed load. It will be negative at this point, since the load, this is the, in left section we are having an upward force. The beam is experiencing an upward force of RBWL by L. So this will be negative bending moment, and from here we can see left section it is be positive because it's having upward direction. So these two are This section will be this section will be under positive shear force, whereas the right section will be under negative shear force. So we'll be having WL by 2 here and WL by 2 here, and we'll connect these two, and we'll find that this point, center point, is will be having no force because the shear force will turn direction from here to here. So again, this is bending moment. Bending moment is WL by 2 into L by 2. So WL by 2, this will be having maximum bending moment this point. This will be having WL by 2 into 0. Again, the WL by 2, WL by 2 into 2, WL by 2 into 0. So these two, point A and B, will be having 0 bending moment, while this point will be having WL by 2 into L by 4, because this will be force acting at this point of quarter of this force. So we'll be having maximum bending moment at the center point, W L square by 8. Again, we can see this is a quadratic equation, and when this is quadratic equation, the the graph will be curvilinear rather than straight line. So this is the second order degree representing curve. So we can draw bending moment diagram 0 to WL square by 8 to 0. So this is uh, bending moment diagram of simple supported beam of UTL. So we can now combine different conditions, and another we have to take different conditions, and we will solve different conditions in order to have we will have to take different conditions, and we will solve these conditions. So uh, on our own, another condition is that if the simple supported beam is experiencing couple or moment, so we can see there is no direct loading, no shear force, or no direct force is acting except one moment is acting. So in that case, the moment is trying to is trying to sending this beam downwards. Otherwise, the in other terms, we can say the beam is experiencing hogging. That means curved surface is going upwards. So the bending moment will be negative. Whereas for shear force, we can see that is uh, shear force is uh, also negative, because the left section is under uh, force that is acting downwards. Left section is under a negative bending moment. So bending moment is trying to give a hogging shape to the beam. So we can see here that bending moment, shear force is negative from here to here. As we discussed, there is no other force except this one. So this is acting down, this is acting upwards, this is acting upwards, and this is again balanced by downwards. So this is negative from here to here. All along the way, shear force is negative. In case of moment is acting, only one moment is acting. And in case of bending moment, we can see that bending moment is acting at this point. So from here it will be maximum, and from here to here, and again this point will be minimum, 0. So these 2 points will face negative 0 bending moment, whereas this point will be having maximum bending moment. So this way we can see bending moment start from here to here. This is all of a sudden jerk is there. So this will be changing sign, and again this will come to 0. So this bending moment is calculated MB by L into negative MA by L, because of this MA by L, and this is MB by L. So this way we can find the bending moment diagram in case only moment is acting, on case couple or movement is acting on the beam. So for the time being, I am signing off. I hope everything is clear to you. Again, I repeat, if you are having any difficulties, you may get in touch with me. Okay, bye.